Hi, my name is Sergey Levine, and today I'm going to talk about robotic learning with large datasets towards general purpose models for all robots. So, if we look at how AI used to work in the olden days, we would have a separate model for each kind of task. For example, we might have one model that looks at an image and produces a semantic segmentation of that image. We might have a different model that looks at an image and produces a classification, another one that generates a caption. Maybe we'd have some kind of visual question answering model that looks at an image and a question and produces an answer. Something that looks at text, estimates the sentiment, a summarization model. So every task would have its own separate model that would be trained on its own separate data. Increasingly, the way that AI tends to work today is that we take very large and unlabeled or weakly labeled data sets. We use them to train some kind of giant unsupervised or self-supervised model, what some people call a foundation model. And then we take that model and we somehow adapt it to a particular specific task, typically using a smaller amount of data or the same amount of data as before, but extracting better performance from leveraging all that pre-training. And that could be done by fine-tuning that model, or it could even increasingly be done simply by few-shot prompting that model to basically specify the task for it. And of course, it's pretty widely known at this point that this is a really great recipe, for example, in NLP, where you can train a language model that can do lots of different NLP tasks. Also a good recipe with self-supervised learning and computer vision, where you can pre-train representations to do lots of vision tasks. But the other trend that we're seeing in recent years is the increasing consolidation even across modalities, where we might have a single model that can process language, images, and maybe even other modalities. This is an example of a recent paper by some of my colleagues at Google called Palmi that adapts language models and gets them to be able to read in images so that you really do have one model that can solve a variety of visual and textual tasks. So this is really a talk about robotics, and my central claim is that perhaps the same kind of consolidation in the future will happen in robotics, although it presents some unique challenges. So the way that robotics, or at least robotic learning, works now is that for every kind of robot and every robotic task, you might again have a separate model. Maybe you have a PR2 pancake making model, a Barrett Wham pancake making model, a UR10 box picking model, whatever this is, etc., etc., etc. So every robot, every task, perhaps even every scene, you would train a separate model, just as before, on data that is specific to that particular kind of problem setting. Well, perhaps in the future, we will have large data sets of unlabeled or weakly labeled data, perhaps of robots, perhaps of other sources from the internet, that will be used, just as on the previous slide, to train a giant unsupervised or self-supervised pre-trained robot model, a kind of robot foundation model, if you will. And just as before, perhaps that model could be adapted with either some amount of fine-tuning or even prompting to perform a particular task in a particular scenario with a particular robotic platform. And the question really in this talk is, what would it take to build such a general purpose robot model? Well, okay, so we have to think about data and we have to think about models, and we also have to think about algorithms. Now, remember, a lot of the driving force behind the methods that led to this kind of consolidation in other fields has been the ability to leverage very large data sets and also weakly labeled data sets. So the data needs to support the kind of broad foundational generalization that we want to see. It needs to be diverse enough to support whatever robot you might want to use. It needs to cover a range of environments because, of course, all these robots doing all these tasks will be situated in different settings. And it needs to cover, of course, a range of behaviors. And the model that is trained on this data needs to be able to, of course, consume all the data. It needs to be scalable enough, and that's no small feat. It needs to be flexible enough to repurpose to new tasks, either with fine-tuning or direct prompting. And it would be very nice if it could perform at least some tasks in zero shot. Now, before I get into the models and data sets discussion, I do want to talk a little bit about algorithms, because it's important to remember that much of this consolidation in NLP, vision, and other fields has also been driven by the ability to utilize unlabeled or weakly labeled data. Now, that's a lot harder to do in robotics, for example, if you're doing imitation learning, right? So classically, the easiest way to leverage data in robotics is to take data that demonstrates the behavior you want to see, and then essentially copy that data and hope that you can generalize if you copy enough of it. But this kind of goes against that ethos of being able to leverage weakly labeled or unlabeled data. And of course, the equivalent of weakly labeled or unlabeled data in robotics might be autonomous exploration, data that robots gather on their own, which is of much lower quality. And then imitation learning won't cut it, so we might need other algorithms like offline reinforcement learning. Now, offline reinforcement learning is basically a way to use large amounts of low-quality data from robots, much like self-supervised algorithms leverage unlabeled data from the web, to get something more optimal than what was observed. So the analogy to the picture above for offline RL is that your data kind of goes all over the place. It doesn't necessarily go from the start to the goal, and then you're going to put together the parts of the data that illustrate the behaviors you want to see to get one behavior that's more optimal than any single trajectory seen in the data set. Now, in the works that I'm going to discuss in this talk, we're going to use both imitation learning and offline reinforcement learning. They're not mutually exclusive, and you can definitely combine them. In some cases, it's not too bad to get demonstration data. In other cases, you really want to be able to leverage suboptimal data. I will talk a little bit more about offline RL, though, because while imitation learning is something that I think many people are familiar with, it's pretty straightforward, offline RL is maybe not something that as many folks are familiar with. So I want to explain a little bit more what it does, what the offline RL workflow looks like, and what the algorithmic challenges are. Now, I just want to emphasize that offline RL is a much more practical way to have scalable robotic learning than online reinforcement learning, because of course online reinforcement learning requires us to interact iteratively with the environment, and this needs to be done many, many times. That's fine if you're learning a single narrow task, but if the whole point of training these large-scale, highly generalizable models is to get them to generalize across many tasks and many environments, performing online reinforcement learning would require iterating through all of the different environments and tasks and so on every single iteration of this iterative online RL process. And that's not really practical. So what we'd really like to do is collect all this data and then use it many, many times for many, many updates to train up our model. So we want to get away from the on-policy RL approach where we throw out our data after updating on it, and instead employ an approach that structurally looks more like supervised learning, where it just takes some existing data set and distills out the best possible model from it, but that has that benefit of RL where it actually distills out a skill that is better than what you would get simply by imitating the data. And that's basically the promise of offline RL. So offline RL takes a buffer of data, just like supervised learning, but instead of copying that data, it actually uses it to discover better strategies than what was demonstrated, perhaps by combining bits and pieces of different behaviors that were seen in the data. And of course, after you run offline RL, you could then perform additional online RL fine-tuning when you want to adapt that model autonomously to the particular task you want to do. And we'll actually discuss some examples of that in this talk. So the workflow if we were to use offline RL would be to collect the data set using any policy or mixture of policies. So that could be like humans controlling the robot, existing hand design controllers, maybe even random behaviors, or any combination of the above. And that would only be done once. And as you collect more data, you can just agglomerate, you can just add to it. And then run offline RL on this data set to learn your policy. And you could kind of think of that as the best policy that you can extract from the data that's provided to you. And then you could deploy that policy in the real world. You can fine-tune it online. You can utilize this as this foundation model for downstream tasks. But if you're not happy with how good it is, then you can go back to step 2 and retrain the model, reusing all the same data you had before. Okay, so that's really nice, but what is the challenge with offline RL? What's the algorithmic difficulty? Well, the fundamental problem that offline RL has to deal with, which imitation learning does not have to deal with, is the problem of counterfactual queries. Essentially, if you're asking the algorithm to discover the behaviors that are better than what was seen in the data, but by leveraging a static data set, then you have to essentially answer counterfactuals. If all of your data, for example, has examples of cars driving on the road, maybe they're not all driving perfectly, but they're generally staying on the road, answering the question, what would happen if the car were to swerve off the road, is actually very difficult because you've never seen that happen. So is this good or bad? Well, how do you know if you didn't see it in the data? The answer is you don't. You don't want to permit counterfactual queries for the kinds of questions to which you have no way of generalizing. Online RL algorithms don't have to handle this because they can simply try this action and see what happens. Offline RL methods have to somehow account for these unseen or out of distribution actions, ideally in a safe way. So you don't want to permit them to attempt to go off the road, but at the same time, you still have to allow them to use generalization to come up with behaviors that are better than the best things seen in the data. So you don't want to constrain them so much that they don't generalize at all. And that's basically the fundamental tension with these methods. Allow them to improve through generalization, but don't allow them to attempt to generalize so broadly that they couldn't possibly get the right answer. And there are a variety of approaches that have been devised to address this. I won't go into the algorithmic details too much. I don't want to present a lot of math in this talk. This is a more high-level discussion. But I do want to talk about the kind of themes that algorithmic solutions to this problem have leveraged. So there are several different methods, but similar principles seem to be effective. So generally, the most effective current offline RL methods are based on value-based RL algorithms like Q-learning or Q-function actor critic that somehow address these unknowable actions, typically by not permitting them. So somehow understand what are the actions to which the neural net will generalize, and for anything to which it will not generalize, don't allow that action to be taken. So there are a few principles that have been effective for this. One principle is pessimism, which basically just states any action that is out of distribution should be assumed to be bad until proven otherwise. And that's a very powerful principle that can be instantiated with relatively simple algorithms like conservative Q-learning that will essentially teach the model that actions that it didn't see before shouldn't be attempted, but actions that are similar to ones that it's seen before, meaning actions to which the network will generalize successfully, those could be attempted. Another approach, which is related but actually very different implementation-wise, is to use what are called policy constraints, where we don't actually assume anything about the value of out-of-distribution actions. We simply don't permit them altogether. So the pessimism actually teaches the Q function that out-of-distribution actions are bad. Policy constraints simply prevent those actions from ever even passing into the Q function by instead constraining the policy. And there are a few methods that have done that. And then there are a few recent approaches that are maybe a little bit more exotic and based on somewhat more nuanced principles, like IQL, for instance, that actually avoid not only all out-of-distribution actions, but in fact entirely avoid out-of-sample actions. They basically formulate new RL update rules that only use those actions that are in the data set and never, ever even have to go outside of that, using things like implicit TD updates based on expectile losses. And those can actually work really well. They're a little harder to analyze, and they're very new, but they can be very effective. But the theme around all of these approaches is that we're going to address this problem of counterfactual queries by somehow discouraging the algorithm from taking the kinds of actions to which it cannot generalize. And then you can maximize over all the ones that you can generalize to. Okay, so that's kind of a whirlwind tour of the algorithmic basics. Now, the methodology that I'll discuss in this talk, most of it will focus on data sets and models, and some of it will use offline RL algorithms, and some of it will use imitation. And generally, the offline RL methods might be desirable because, well, they will allow us to actually do better than the typical behavior in the data, although they can be a little bit more complex. And in reality, we'll often mix and match these things. So let's get to the meat of the talk and talk about the kinds of data sets and models that can allow us to start getting at these kind of foundational robotics models that can generalize across tasks, across embodiments, and across robots. Now, I'll say right off the bat that we haven't accomplished this yet. So what I'm going to talk about are some initial steps towards this direction, and these steps can give us some hints about what an eventual solution to this problem might look like. But none of the methods I'll describe actually cover all the bases just yet. So I'll first talk about our work on something called the bridge data and a project called Pretraining for Robots, which is going to be for now limited to a single robot. It's actually a low-cost robot called a Widow X, but it will cover many environments and many tasks. The models here won't be prompted or goal conditioned in any way. They'll actually just be conditioned on a task indicator, but we will study fine-tuning in detail here and understand how imitation learning and offline RL compare when used for pre-training and fine-tuning. Then I'll discuss some work that extends this, the bridge data to incorporate very effective fine-tuning with RL. So there, we will still have only a single robot, but we'll extend these models to be conditional on goals so they can leverage any data without requiring task annotations. And that will actually enable some new fine-tuning methods that are very effective and can actually fine-tune it through autonomous exploration. And then I'll talk about some work that studies generalization across different robots in the domain of robotic navigation. So there I'll talk about a model we developed called GNM, Generalized Navigation Model, as well as extensions that allow it to be fine-tuned to other tasks. So there we will have different types of robots, although they're all solving navigation tasks. It's debatable as to whether there are many tasks or one task. The tasks are all going to be navigation tasks, but they will be promptable and goal conditioned, and they'll actually be fine-tunable. So let's start with the bridge data discussion. So before we can really get into studying the methodologies for designing these foundational robotic models, we need a suitable data set to get us started. So to that end, we have a large ongoing effort in my lab to collect what we call the bridge data. This is meant to be a community resource for a large data set that will enable somebody, when they get a particular robot in their lab, for now it has to be our robot, of course, it'll enable them to take a data set that contains a variety of past interactions, past tasks, past environments that'll bridge the generalization gap for their robot, so that in their domain, perhaps they only need to collect a small narrow data set, but then they will include all this past bridge data to enable broad generalization. So the bridge data set currently contains about 33,000 demonstrations in 20 plus environments and over 100 tasks, although the data set is actually rapidly expanding and we're actually working on a large scale up in the near future that will raise the number of demonstrations up to 50,000. And it's designed to be reusable by other researchers in new domains and for new tasks. And what we've done to make it maximally reusable is to include many different environments and many different tasks in the hopes that if the environment in your lab is different from ours, perhaps the range of environments sort of covers that distribution. We've also made the deliberate choice to set up many of the environments around these toy kitchen settings that could be bought from Amazon so that other labs can buy similar toy kitchens. They don't have to be the same, but at least they'll be within the distribution. So that also helps to bridge the gap across different domains. And we've actually verified with our collaborators that other labs have been able to set up experiments with the bridge data set in their own facilities. We also have, of course, many tasks because each lab might want to do a different task, and the range of tasks is expanding every day. All of these are collected with a low-cost robot. This is called a Widow X250S from Prof and Robotics. It's a cheap robot. It's about $3,000. And again, the aim there was to make something pretty accessible that would have a low barrier to entry that just about anybody could get. We are, in the future, thinking about extending this to multiple different embodiments, but for now it's just for this single embodiment, which we opted to make a low-cost and relatively accessible robot. So I'm going to tell you about a particular project we've done that leverages the bridge dataset called PTR. PTR stands for Pretraining for Robots. That was meant to study how offline RL can enable effective pretraining on this dataset for very efficient downstream fine-tuning. So the idea in PTR is actually very simple. We're going to take the bridge dataset and we're simply going to pre-train a single policy with offline RL to perform all of the tasks. And the task conditioning here is very naive. We simply use a one-hot indicator where that is passed to the policy in addition to the current image observation that indicates which task the robot is doing. And the last entry in that one-hot indicator is reserved for the fine-tuning task. So we're not doing any kind of text conditioning or role conditioning yet. That will come later. But for now, we're just conditioning on this one-hot vector. So we pre-train on all the tasks together. And then when we get a downstream task, we simply use that reserved last position in the one-hot vector and train the policy some more using a small amount of data for this new task. It's going to be between 10 and 20 trajectories, very small. And we actually keep recycling the old data through the model so that it doesn't forget it, and that gets us this fine-tuned model. Now, we can use this in a variety of ways. We could, for example, adapt a skill that was seen in the bridge dataset to a new scene. So maybe we had some door opening tasks before, and now we have a new door that has to be opened in a structurally similar way, but it's different. And we can collect 10 to 20 trials here. I think this is done with about 10 trials. And use PTR, and we get about 60% success rate with just 10 trials, which is pretty good. And if we compare that to other alternatives, it is actually quite a bit better. So if we use behavioral cloning, regular imitation learning, it's about 10% lower. If we use joint training with RL, then it's quite a bit lower, it's 25%. So there's an improvement to be had both from using offline RL and from actually performing the fine-tuning. We can also fine-tune to entirely new skills. So this is a new environment with a new behavior. Put a cucumber in the pot, although of course the behavior is structurally similar to the one seen before, so the robot has placed other objects in other kinds of pots. And here again, for these kinds of tasks, PTR actually ends up working pretty well. And notably, it improves over imitation learning. It actually improves more when the skill is more different. But perhaps more interesting for this discussion are the right two columns in this table, R3M and MAE. These are two previously proposed representational learning methods they're basically computer vision techniques that leverage the same prior data as our method, but use it to learn visual representations rather than to pre-train policies. So you can think of this as sort of applying the more classic self-supervised learning approach from computer vision to the robotics problem. And you can see that the performance of these methods is quite a bit lower, which means that we are really getting a lot of mileage out of pre-training with offline RL in particular. So this really indicates that the robotic foundation models need to be trained with robotic techniques. Like we can't just take the kinds of unsupervised or self-supervised methods from other areas and apply them to robotics. We get a lot more mileage out of leveraging the fact that these are really control problems. And I think this bodes really well for the prospect that we would have offline RL trained foundational models in robotics that can leverage lots of robotic data, perhaps also other sources of data. Of course, another thing that's really good to check here is that we are enjoying the benefits of scale. So we all know about scaling laws, that larger models with larger data sets tend to perform better. And indeed, we see those effects here as well. So the x-axis here is roughly corresponding to model capacity, starting with a small convnet, a 3-layer CNN based on the Impala architecture, and then ResNets of varying sizes. And the y-axis actually shows a success rate at the downstream fine-tuning task. So we pre-train with models of different sizes, then fine-tune, and then measure performance. And you can see that especially for the harder pick-and-place task, performance actually continues to improve as we make the models bigger and bigger. So that's really promising. And it's important to remember here that the data for these experiments, the bridge data, was not collected for offline RL in mind. It was actually collected primarily for imitation learning, but offline RL does do quite a bit better here. So this gives us some hint that perhaps these kinds of RL techniques can be pretty effective for training up these models that can then be fine-tuned to individual tasks. Now, of course, here the task specification is done through these one-hot vectors, reward functions, etc. This is not really providing all of the capabilities that I motivated in the beginning. So let's try to lift some of those limitations. Let's introduce more flexible task specification by prompting the model with goals. And let's also study how the fine-tuning itself can be made autonomous. Because for PTR, the fine-tuning data was provided by a person. It consisted of demonstration trials. What if we can fine-tune autonomously? So what we're going to do in the next project called FLAP is we're going to introduce goal conditioning, longer tasks, and autonomous RL fine-tuning. To that end, we're going to use the bridge data, and we're going to train three separate models here. We're going to train a goal condition policy. So the goal condition policy takes in the current observation and an image of the desired goal. So it makes no additional assumptions. The assumptions are actually weaker. We don't assume that we have a ground truth reward function or a task indicator anymore. Instead, we prompt the model with a picture of the goal. But when we place this model in a new environment, it might not succeed in zero shot, so we might need to fine-tune the goal condition policy, and that's where these other two models will come in. So the way that we're going to solve a downstream task is not by directly prompting the goal condition policy and forcing it to do the entire task, but instead by planning a sequence of subgoals and prompting it with subgoals. The state encoder provides a representation over which we'll plan. So we don't plan over raw image pixels. We plan over an encoded state, which is acquired in the process of training the goal condition policy. And the affordance model is essentially this higher level model that tells us which subgoals can be reached from which others. So let's dig into this a little bit more. The structure of the system is the following. We have an encoder phi that reads in a state, and it produces some latent representation. This latent representation is then going to be modeled by an affordance model that predicts which future subgoals, z prime, can be reached from which embeddings of current state z, based on latent codes that are sampled from a Gaussian prior. So the affordance model is essentially a variational autoencoder for those of you that are familiar with it. For those of you that are not familiar with it, just think of it as a higher level model. It predicts some number of steps in the future, which future subgoals can be reached and which can't be. And we can optimize over the latent codes here, U, to create a sequence of subgoals in this encoded space Z that are reachable from each other and that correspond to embeddings of some unknown states. And then we can pass these to our goal condition policy so that it executes those steps one by one. The latent codes are trained end-to-end as part of training the goal condition policy. So they essentially represent the information that is necessary for the goal condition policy to figure out what the value is. So that basically means that they are lossy representations of just the information you need to figure out how to reach something. So that's the architecture of the method. The way that this is going to be used is that when you get a new subgoal, when you get a new final goal, you're going to plan subgoals using the affordance model and then execute them one by one. But crucially, the goal condition policy might not succeed at reaching each subgoal in a new environment. So then what you can do is you can use those subgoals to fine-tune the goal condition policy. So essentially the subgoals scaffold the automatic fine-tuning on the downstream task. And it's kind of reasonable to surmise that this would work. It's essentially saying that maybe it's easier to figure out subgoals for a new task than it is to actually perform that task. If I see a new door that I've never opened before, I might imagine what the door looks like when it were open so I can have the subgoals in mind. I know I have to grasp a handle somehow, I know I have to pull on it, but figuring out the mechanics of actually grasping the handle is something I could do with automatic fine-tuning. So here are some results that illustrate the benefit of this. Here the task is to put the pot on the left burner and then put the bunny in the pot. So we're, I guess, cooking the bunny. Model free RL generally doesn't succeed at this without the structure. If we run our planning approach with these subgoals, but do not fine-tune the policy, then we get a 25% success rate. But if we then take those planned subgoals and furthermore use them to fine-tune the low-level goal condition policy, then the success rate goes up to 75%, and the robot can actually perform this multi-stage task. Here's another example. Here the robot should put the knife in the pot and the sushi on the plate. If we just attempt to do the task in zero shot, it kind of has a rough idea of what's going on, so that suggests that the subgoals are reasonable, but physically it really struggles to pick up the knife and it doesn't tend to drop the sushi very accurately. But if we let it fine-tune further, then it can do the task about 50% of the time. Still far from perfect, but a lot better than if it were to try to generalize in zero shot. So this suggests that if we train up representations of affordance models and goal condition policies together, we can actually get a system that can effectively fine-tune new skills and can actually do the fine-tuning autonomously. All right, now so far everything I've talked about uses the same robot. In the next project I'm going to discuss, we'll see how we can build models that can actually generalize across different robots and even generalize to new robots in zero shot. Now, we're going to do this in the domain of robotic navigation. That is, of course, easier because arguably navigation tasks are more structurally similar to each other, whereas different robotic arms might manipulate objects differently. So this gives us a gentler way to get started on this problem. We're going to learn to navigate from diverse data, and the approach is actually going to be quite similar to the one that I discussed in FLAP, where we're going to have goal-conditioned policies. So the setup is that someone gives you a picture of the destination, maybe a picture of their front door, and the robot is supposed to navigate the environment to reach that destination. So find and navigate to a given goal landmark using only camera images. You have your current observation, you have your goal, and you have to figure out what goes in the middle. Now, I'm going to show a lot of aerial views when I present these results, satellite pictures. Those are not actually available to the robot unless stated otherwise. In some cases, we will actually give it satellite views, but most of the time we won't. I'll tell you when we do. But the satellite views, in many cases, will be presented for your visualization. So how does the method work? Well, again, it's very similar to what I discussed before. We're going to have a network that takes in the current observation and the goal, and is going to predict the distance in time steps and the action to reach the goal. And just like with FLAP before, we don't want to directly command the final goal to reach because that might be too hard, it might be too far away. So instead we'll use a planning algorithm. In this case, the planning algorithm actually uses a topological graph. So the observations that the robot has previously collected in this environment will be used to connect up a graph where the edge weights on the graph are the distances predicted by this model. So it's not a full reconstruction of the environment, it's not running SLAM, it's just taking individual images and linking them up using the learned model. It's a very lightweight graph-based planning algorithm. And then when it gets a new goal, it connects that goal to the graph, again using the same model, using the distances from the model, plans through the graph, and then goes to the first waypoint. So at a high level, it's just planning over subgoals, just like the method from before. It's just that in this case, the plan is not constructed by continuously optimizing the subgoals, but rather by using a PRM-inspired kind of graph. The initial version of this project was actually trained on 40 hours of training data that was collected for an entirely different project before that. So this is also using an offline training procedure, and it worked actually pretty well. Now, one of the more recent incarnations of this approach before we jumped into studying multi-robot learning was to try to scale it up to kilometer-scale navigation, where we actually did start giving the satellite images to the robot. So here we give it its first-person view and satellite pictures, and it could navigate for up to a kilometer. If we give it intermediate checkpoints, it can follow hiking paths that are up to 2.7 kilometers in length. It can deal with errors in the map. So here a semi-truck was parked at a place that used to be traversable in the satellite view, and the method can route around that. And it can leverage the satellite view when it's available, shown in blue. When it's not available and it only has GPS, it can still try to find its way around the environment, shown in pink, but has to backtrack more often when it encounters dead ends. So it's possible to incorporate higher level navigation into this, and it actually works pretty well. But of course, the main question that we're concerned with in this work is, can we train one policy to control many robots in this way? So the approach here is actually going to be very straightforward. We'll just adapt these goal condition policies from before. We'll train them on data from 6 different robots, actually 8 separate data sets, which includes robots ranging in size from small-scale RC cars to full-scale ATVs. The policy is still a goal condition policy. The only difference is now we give it a little temporal context, a short sequence of frames. And the role that serves is it essentially lets the policy figure out what kind of robot it's controlling. So we don't explicitly actually tell it any parameters of the robot, but by observing this temporal context, it can roughly figure out how the robot behaves. So it can figure out if it's making sharp turns or not, roughly how fast it's going, that sort of thing. And it turns out that that's actually enough. This kind of implicit system ID is actually sufficient for it to be able to generalize across robots, which is perhaps a little surprising. And then we're going to deploy this policy. We're going to deploy it on the training robots. We'll also deploy it on new robots that were never seen during training. And we found, perhaps surprisingly, that this allows more robust navigation. It allows generalization to new robots. It also allows the existing robots to generalize more broadly because even for the training robots, they can benefit from data collected by other robots in other settings. Here's an example of the robustness benefit of training across many robots. Here we introduce some mechanical damage where we stick this rod into the wheel of our robot. Now this is one of the robots seen in training, but it's never been seen with this mechanical damage. If we just run a regular policy train on only this robot and command it to go to the same location, then after the damage, it can't actually drive straight and ends up veering off the road. But if we use this GNM policy that was trained across many robots, it actually exhibits significantly improved robustness and can actually drive the robot, even with the damaged wheel, successfully to its destination, which in this case is the store. We can generalize in zero shot to a new robot. This is actually a drone There were no drones in the training data. It was all ground robots. Now, the drone here is pretending to be a car. It's flying at a fixed altitude, but it has a different camera. It has this kind of fisheye lens. And of course, the dynamics of the drone are different. And yet the policy is able to fly the drone in zero shot. We can also use this as a basis for fine tuning. And one of the ways we've explored doing this is in this recent paper called Faster Lab, where we take an offline trained GNM policy and then perform additional online training with a very fast online RL algorithm. By initializing the policy with GNM, it already has a lot of navigational common sense. It already basically understands how to drive around obstacles, how to avoid walls and things like that to some degree. And then online RL can get it to drive fast through some circuit. So our goal here is to drive through a particular circuit as quickly as possible. Now, starting off from the GNM initialization, sometimes it drives well, sometimes not so well. So it's learning as it goes. This is doing RL directly from image pixels, and generally RL from image pixels can take hours or even days. But with this initialization and a suitable choice of online RL algorithm, it can actually train in 10 to 20 minutes. You can see after 10 minutes, it's still doing some stupid stuff, but it generally makes forward progress. After 15 minutes in this particular circuit, it actually drives much more consistently. Still not perfect. And then after 20 minutes, it can do the route very well. After enough training, we found this policy actually achieves performance that's comparable to a human operator driving through the same first-person view. If the human gets a third-person view, they can actually do a little bit better, but if they're constrained to use the same first-person camera, then it's about the same. So this overhead view shows a different circuit. This is a much smaller circuit that we set up in between some furniture, but this is convenient if you want to visualize the trajectories. You can see that after 4 minutes, it gets a lot of collisions. After 9 minutes, it avoids the collisions, but is not driving all that well. And after 12 minutes, it learns to stay on the center line and drive more quickly. And this is a lap progression plot, which is showing the lap time on the y-axis and the amount of training on the x-axis. And you can see that after about 15 minutes of training, it more or less got to the best lap times. So that's really promising because that suggests that this GNM initialization can not only generalize to new robots in zero shot when prompted with appropriate goals, but can also serve as a foundation for fine-tuning with very efficient online RL, and that the GNM pre-training makes the RL process much, much faster. So these are the projects that I described. Now, these are kind of algorithmic explorations that are meant to study how we can build towards these general purpose robotic models. But in the last part of this talk, I want to talk about some other efforts that have been done in collaboration with Google on focusing more on the scale of the data and the scale of the models themselves to see how far some of these things can be pushed. This is going to focus less on algorithms and much more on model and dataset scale. So separately from the Berkeley work that I discussed here, we've been working on large-scale robotic learning at Google for quite a while. I started there in 2015. In 2016, we had some results on large-scale learning of grasping in bins, where we had many robots working together to collect a huge data set of randomized grasping and then use that with reinforcement learning to learn better grasping strategies. This was essentially offline RL, although we didn't call it that at the time. So it was kind of offline training with continuously piping in additional online data. But this was in a narrow setting, in just this bin picking setting, for a very specific task. And since then, we've expanded these kinds of methods across the axes of generalization, environment generalization, object generalization, but also task generalization. And I'll tell you a little bit about some of the things that we found out along the way. So perhaps one of the earlier successes of this line of work was the work on robotic grasping. And as I said, that's maybe more narrow in terms of environment, but it was meant to study generalization across objects and robustness. I'll show you some results from a method called QT-opt, which was actually the second method we developed. This appeared in 2018, which was a kind of hybrid offline plus online RL system that continuously collected more data and also reloaded all the data from previous experiments to train up the best possible grasping policy. And this policy already exhibited some pretty interesting emergent behavior. So if, for example, we went in and knocked something out of the gripper, it would attempt to retry the grasp. It was pretty persistent. It could pick up small objects, large objects, objects that were oddly shaped. But the most interesting thing to me was always the kind of retrying behavior, where unlike a conventional grasping system that would sort of plan a path to the goal and then just execute it, this one would actually have this reactivity by closing the loop on vision. And it did pretty well on a variety of really difficult scenarios, picking up objects that were large, small, transparent, oddly shaped, deformable, and so on, and could get a success rate of 96% on a pretty difficult test set of previously unseen objects. Most of the failures were actually on those rubber octopus toys, so if it was not for the octopus, then maybe this would be even higher. But of course, this is in a single task setting. So what we did after that is we wanted to see if some of these ideas, these large-scale RL ideas, could be scaled up to multitask settings, where we now set up many different tasks. They're all kind of themed around pick and place, but they involve different objects placed in different ways. 12 different tasks, thousands of objects, and again, large-scale data collection. And that worked pretty well. And then after that, to further push on this kind of offline training point, we had a new hypothesis. Could we learn these tasks without rewards using goal-conditioned RL? And that we did with offline reinforcement learning using the same data set. That worked pretty well. So this is the goal-conditioned RL result. And here you can see the goal image in the lower right. This actually predates the flap work, so this doesn't have all the planning components yet. This was just kind of the core goal-conditioned RL backbone. And one of the interesting things about this is that we actually studied how this could serve as an unsupervised pre-training objective. So we could take that goal condition policy and we could fine-tune with task reward and show that the goal condition pre-training actually provides a very effective auxiliary objective for speeding up learning a specific task with a task reward. So that's really promising. That suggests that these kinds of goal condition techniques can be used as ways to provide general initializations for other tasks, even tasks specified with reward. Now, most recently, and this is actually work from that was released just a few months ago, we put out our research on massively scaling up this offline RL method for an actual real-world application. And the application that we studied here was sorting recyclables. It's based on very similar principles. The tasks are focused on grasping and placing. But now the job of the robot is to basically sort the bottles and the compostables and the waste. And it's supposed to do this end-to-end with an RL trained policy, collected through a combination of experience gathered in these classroom environments and also actually directly in the real world in real office buildings. Now, there are quite a few implementation details to make this work. At the core of it is essentially the same offline RL technology that I discussed before, with a few modifications, like including features from a computer vision system and so on. But it actually, works in the real world. It can sort the kind of trash that real humans put into the trash bins, and there's results in the paper studying the performance of the real-world deployment. We've also done quite a bit of work most recently on massively extending the range of tasks by incorporating instruction conditioning into these models. One of the works we released, called RT1, aims to enable this using a large transformer model trained on many, many tasks with textual commands. So the robotics transformer, RT1, is essentially a transformer model that reads in a sequence of recent images from the robot, tokens representing the instruction, and then outputs tokens representing the actions. And this can perform a wide range of different tasks based on simple textual commands like put the chips in the drawer, pick up the Coke can, and so on. Now, the commands here are simple and atomic, but by providing the robot with these atomic commands, we could then link those up together into a more complex system, and I'll tell you about that in a second. But before I do that, I wanted to mention a little experiment that we did in this paper that doesn't address the multiple embodiments thing completely, but it provides a hint of how that could work. So we took the data for RT1, which consisted of these kitchen manipulation tasks, and we actually combined it with the bin picking data for the previous projects I described, and trained one large policy on all of it. And we actually found that the robot used for RT1 could actually inherit many of those bin picking capabilities seen in the previously collected grasping data. So we could actually, with a large enough model like the RT1 model, we can actually merge multiple data sources, and it actually does work. And we're investigating now further applications of this concept. But the last thing I want to tell you about is how to take the atomic skills that RT1 can perform and link them up into longer horizon behaviors. And this is going to connect to something that I mentioned at the very beginning of this talk when I talked about how we can train models that combine text and language. So we actually used the PaLM model, which is basically a large language model based on PaLM that has been fine-tuned to also be able to read in images, to act as a kind of planner for longer horizon behaviors. So the idea is that RT1 can process simple atomic commands like pick up the can or put the chips in the drawer, and then PaLM can take a more complex command, interpret it into individual steps, and then command RT1 to perform those steps. And that can allow us to perform some complex things like bring me the rice chips from the drawer. And then PaLM will figure out that, well, in order to do that, you should command RT1 to open the drawer, you should command it to pick up the chips, and you can actually dynamically replan, because when the nefarious human operator here goes in and perturbs the robot to prevent it from correctly picking up the chips, PaLM will say, okay, well, now you have to try picking up the chips again because that didn't work. So I think this is an interesting kind of side note to the story about general purpose robotic models, that once we have those foundational behaviors, for simple atomic skills, linking them up into more complex behaviors can actually be done using the kinds of large-scale models that have been so successful in other applications domains as well. So to conclude, I think we will increasingly see this kind of consolidation in robotics that we've seen in other fields, where we'll move away from individual task-specific kind of controllers towards general models that have been trained on many skills in many environments and perhaps across different robots that can utilize their broad and generalization capabilities to enable very rapidly acquire new tasks, perhaps for new platforms or perhaps in new settings. All right, I'd like to thank my collaborators, all the students that were involved in this work. I'd like to also thank you for listening. So thank you very much.